the subject, just want to use one slide to really motivate why studying this kind of systems. So we've seen the great breakthrough we had in 2017 with the first detection of binary star merger. And in particular, I want to stress the fact that we observed also a short gamma burst together with that. So this confirmed the long-standing hypothesis connecting binary star merger and short gamma burst. But besides this great success, this left behind for us, for theorists, big questions about how a binary star merger can produce a jet in the first place, which mechanism, and also which kind of remnant, which kind of central engine do we have? Is that a black hole surrounded by an accretion disk, or maybe a long-lived massive neutron star? We don't really know what happened in this case. And this is really where numerical relativity simulation becomes crucial. It's really the tool to understand these things and answer these big, very important questions. So in terms of mechanism, just a notion here, we basically understood that neutrino-antineutrino annihilation is probably not powerful enough to explain short gamma bursts like these or others that we observed. So we're converging to the idea that we really need a magnetic, the magnetic fields play a critical role, magnetically driven jet. So this seems to require GRMHD simulations. And speaking about GRMHD simulation, investigating this problem, we had some progress and a lot of attention devoted to the case of a black hole accretion disk. And here you see some examples. And if you have massive enough accretion disk, strong magnetic field, you can think this system can power an accretion powered jet by the Blunt's-Knight mechanism. This was mentioned before. And we also mentioned one of the groups even obtained an actual outflow, mildly relativistic, in a magnetically dominated funnel, and this is what I call a mean-severe jet. So it's quite promising. But on the other hand, the massive long-linear star case has been somehow left behind. So there is no, this is only poorly investigated, despite the fact that a large fraction, an important fraction of all binary star mergers, including this case here, might have a post-merger a remnant that is a long-lived neutron star. So with this paper discussed by Bruno in 2017, we started a systematic investigation of this case in GRMHD, and the paper I'm discussing today is continues and making another important step in the same direction. Okay, so coming to the simulation, as I said, the physical setup is numerical also is similar to what discussed by Bruno. I just give a few elements. So this is an equal mass 1.35 binary neutron star with APR4 equation of state, the piecewise polytropic approximation of it, describing matter. And for this EOS and masses, we get a supermassive neutron star. Bruno explained this is something that will collapse the black hole eventually, but on timescale much longer than what we cover with the simulation. And a relevant difference is that here we really want to push the effect of the magnetic field. So we start with initial magnetic energy of order 10 to 48 ergs, which is quite a lot, and putting the magnetic field in the usual way, so purely boloidal initially confined inside the star, corresponding to a maximum strength of 10 to 16 Gauss. So this is a lot. And this continues along the discussion on the resolution. So you know that we don't have enough resolution to capture the main magnetic field amplification mechanism acting on a very small scale, like Kelvin anomalous instability, in particular, and MRI. And so, but we still expect that the post-merger system will have magnetic energies of the level of 10 to 50, 10 to 51 Earth. So, since we have this numerical limitation, having a strong magnetic field allows us to study this very magnetized system that we expect in post-merger, irrespective of how you get to that point, in a sense, even if the first part is under resolved. And this is, of course, not the same as evolving a high enough resolution simulation from the more realistic 10 to 12, 10 to 15, 10 to 13 Gauss binary neutron star up to the magnetization that we expect. So this is a caveat that we should keep in mind, and this essentially applies to any GRMHD simulation of binary star mergers that we have today. So down here you see the first look at the simulation. density snapshots around the merger. Time of merger is 0 here. And then towards the end, you see 95. And the first thing you need to know about this post-merger evolution is that around 50 milliseconds, the system has already achieved mainly axis symmetry. And also, at least on a scale of order 100 kilometers, the evolution in this phase appears quasi-stationary. When we look at larger scale, we notice that in this last 50 milliseconds, 50 to 100 post-merger, we notice that in a range of distances between 50 and 400 kilometers, the density distribution is even isotropic and also seems to not change in time, so even steady. And you see here a scale of 1.6 thousand kilometers. So we're talking about this green area here. Below 50 kilometers, the bulk of the remnant deviates from spherical symmetry. I'll show that later. But up to here, we have this very isotropic system. So here you see, in particular along the axis, density versus time, and at different distances. And you see that after 50 milliseconds, this remains rather flat up to large distances. And in terms of density versus radius, in the same distance range, it is now average everywhere, we get that the density goes as r to the minus 2 up to 200 kilometers. And this corresponds to a steady green solution, and then gets a little bit more steep. So what we're observing here is the effect of a slow, isotropic, rather constant, rather steady, magnetically dominated outflow. And note that here the initial faster dynamical ejecta at this time already left this domain. So all the matter you see here belongs to a post-merger phase of matter outflow. And here, just to convince you about being magnetically driven, you can compare the cumulative mass outflow at the sphere of 150 kilometers versus time. That's the dynamical ejecta contribution for the simulation at hand and the non-magnetized equivalent. And you see how this gets much, much larger, while this contribution is much smaller. So this confirms that the build-up of magnetic pressure associated with magnetic field amplification is the driver of this kind of outflow. So the first thing to know is that if you have a strongly magnetized post-merger, long-lived neutron star remnant, this will be surrounded by a very heavy, very dense cloud, an isotropic cloud of material. Okay? So coming to magnetic fields, here we have magnetic energy evolution versus time. This grows by 3 orders of magnitude and goes across different stages of amplification. So we have a pre-merger amplification. This is a matter of debate. We proposed some explanation in the previous paper, also not very important for us now, so I'm going to skip. And then, when the two stars touch, we have Kelvin-Hamilton instability, strongly amplifying the field, mostly in the toroidal component, which dominates for a few milliseconds. Then MRI takes over as the dominant mechanism, still amplifying the field for another few tenths of milliseconds. And what is interesting is that around 40 to 50 milliseconds, we observe a saturation of the magnetic field growth. So, coming back to the problem of the resolution, we know that we don't have enough resolution to solve. We are very far, actually, from a resolution that captures Kelvin-Hamilton stability, as shown by the group, the Shibata group papers. So we should expect something much steeper here. But when we go on with the MRI phase, then the situation gets better. And what you see here is comparison between the wavelength of the fastest growing mode of the MRI compared to the grid spacing. And essentially we have that white means 10 points and purple means 1,000 points to cover your lambda MRI. So at 30 milliseconds after merger, we are already in a situation where we're essentially able to resolve the MRI everywhere in the system except from the inner region inside the 10 kilometer radius. But I'll show you later that the actual rotational profile of the remnant is such that up to 10 kilometers, you have an angular velocity that grows with the cylindrical radius. And this is a situation which the MRI wouldn't develop anyways. So this is not relevant for MRI anyways. So this gives the impression that irrespective of how we got there, after 30 milliseconds, we have a system that we can resolve, we can describe reasonably well. Okay? And this gives confidence that this saturation is a physical saturation. Okay? And actually, this was already observed also by others. In particular, the Shibata group did shorter simulations, but with much higher resolution, and they also observed this sort of saturation with a much deeper Kelvin-Helmholtz mitigation. And this is at a level a little bit higher than this. So what we have here might be not far from really the maximum magnetic energy that you can have in a binary star merger in general. Okay? All right. So if we look at the magnetic field configuration, we have the, so I put this CN sphere of radius 10 kilometers to give an idea of the size of the scale. What we have is a formation of strong toroidal field in the equator, which is expected, up to 10 to 16 Gauss strength. But also, interestingly, we see the development of this helical structure along the axis, along the spin axis, with toroidal field of order 10 to 15 Gauss. This is actually, this type of structure are actually promising for shocking advanced jet. However, it looks like this kind of structure don't persist, and the interaction with this cloud of more turbulent cloud of material that is surrounding the bulk of the remnant neutron star destroys this structure. So this doesn't persist. Okay. And okay, this was just to emphasize the kind of helical structure. When we go to larger scales, we see something interesting. So here we still don't have the helical structure. This is toward the end. Don't have a helical structure would be favorable for a jet, so this is not happening. But we notice something else. We notice single magnetic field lines extending up to 100 kilometers along the axis. This is a single magnetic field line. So this is important because it looks like a global magnetic field structure is emerging, or might be emerging, supporting the idea that a long-living neutron star formed from binary star merger could end up being, at the global level, a magnetar-like diamond field. So I think this is a relevant result. Okay, let's come to the main point. That is, what are the chances of this system to power a shrunken reverse jet? Well, 100 milliseconds after merger, we see no signs of jet formation. We have this heavy magnetized outflow, in particular along the axis. This is non-collimated, non-relativistic, and also, if you take the ratio of magnetic pressure over fluid pressure, in most of the volume, this is between 0.1 and 10. So this is not something that we would call magnetically dominated. Accelerating this material to transform it into a jet would cost, because this is very heavy, would cost huge amount of energy. So we cannot hope that this will turn into a jet somehow. Instead, this material represents an obstacle for any possible jet, incident jet, launched by the remnant at later times. So costing additional energy to drill through it. Okay? And also, the fact that to launch a jet, we would need, along the axis, much lower density. So something has to change there. But we've seen that up to large distances, the densities remain high, and it's rather constant over 50 milliseconds. So if something's going to happen, and this will produce a jet at a later time, this will probably take a much longer time scale than 50 milliseconds. Okay? At small scale, the density distribution at early times, is 10 milliseconds after merger, reveals the structure that is already observed by many authors. We have a compact bulk or core of the neutron star with an outer layer that is more torus shaped. And in the literature, a lot of people tend to refer to this as a neutron star surrounded by an accretion disk. But actually, this is not an accretion disk in the same sense as an accretion disk that surrounds a black hole. This is a unique object, continuously attached, where we have some centrifugal support that is higher in the outer part, and where viscous effect consume or remove part of the centrifugal support, and in the long term tend to make some material migrate towards the center. So this is not an accretion in the same sense as a black hole disk accretion. Okay? So I would be cautious in calling this an accretion disk. So this is just a note I wanted to make. But what we see is that a few tenths of a millisecond later, this structure is gone. So this system is continuously losing some material. We have this magnetically powered outflow. And also is losing this initial shape and get more isotropic. So this is what we have 70 milliseconds after the measure. So here there is nothing that looks like an empty funnel or low density funnel along the axis, or anything that could suggest that a jet can be launched here. So it doesn't look very good for a jet. In terms of energy, the main energy reservoir that could possibly power a jet is rotational energy here. And here you see the profile of angular velocity versus cylindrical radius. And this is also something that was observed in other previous simulation. We have a relatively slowly rotating core with an outer envelope that is faster rotating. The maximum is around 12 kilometers. So this is the part where MRI is not active. It's only active in this part. And after the maximum, this goes down, and it's very similar to a Keplerian profile. So this means that all this material is almost orbiting. It's not supported by gradient of pressure, but it's mostly centrifugally supported. So also the reason why these systems, which still have a mass larger than the TOB maximum mass, doesn't collapse is not because the core is supported. In the core, the density profile is very similar to a TOB actually. But because all this material is centrifugally supported, this is what prevents the collapse, at least for the time being. So in time, this rotational energy this differential rotation is consumed with the maximum going down and the core gaining a little bit. And this will at some point meet halfway. And we estimate a timescale from this of 150 milliseconds. But we don't use this number to make any claim because the lack of resolution here is such that we don't really trust a timescale for this. We trust the picture. We trust the general behavior, okay? The qualitative picture. And this consumption of differential rotation corresponds to a decrease in rotational energy that is rather linear over the last 15 milliseconds. And this is a lot of energy. So we might wonder, where is this energy going? And we found out that less than 1% of this amount of delta Eroth goes into radiokinetic energy of the flowing material. So this is very little. And magnetic energy variations are also of the order of 1%. While most of this energy goes into the rearrangement and heat of the remnant. In particular, the fact that we have this outflow material, continuous outflow material, is actually making the system less bound. So positive gravitational binding energy variation is taking up part of the energy that comes out of here. And the final note is that the energy, rotational energy at the end of the simulation is still very high, and also magnitude higher than what would be needed for the jet core kinetic energy to explain extraordinary bars like 1708, 17A. But the problem is that so far we didn't see any efficient conversion mechanism. And there is only little hope that something will drastically change at later times. So for the time being, for the results that we have, it looks like the scenario in which a long-lived neutron star powers a short-wave burst is the stable. And maybe in the last minute, I want to comment on another thing we did in the same paper. We performed another simulation that is exactly the same, up to 70 milliseconds. But then, at precisely 72 milliseconds, we induce the collapse of the remnant to a black hole, just by changing the equational state of supernuclear densities, leaving the rest unchanged. just an experiment to see what the black hole formation would, what's the impact of that. And you see the comparison 5-6 milliseconds later and collapse between the two. And the first thing to notice is that from the relative difference in density, when you form the black hole, only matter within 200 kilometers from the center is affected by the collapse, while all the rest doesn't even know, doesn't feel that there is a black hole forming. And we form a black hole of 2.5 solar masses, dimensional spin not so high, 0.5, and still surrounded by a disk that is mass of order 0.1 solar mass. And this is usually the kind of mass that is considered enough for a black hole disk to be candidate to power a jet by the Blankos-Knight mechanism. And indeed, if we put in the numbers, also thanks to the fact that the poloidal field close to the black hole is very high, 10 to 16 Gauss, we have a very high power. And we also did the experiment, since we have this very heavy material, very heavy layer of material along the axis that you need to drill through. This is a powerful jet, but we were not sure, so we made an estimate to check whether this would be able to drill through despite this dense layer. And this depends on the initial angle, but for realistic range, this should be able to drill through. So this would also lead to possibly a successful jet. And okay, we learned other things. I want to just give the last point on this last topic, about the mass of the disk that you form. So there are studies addressing the question of what is the mass of the disk left when you collapse a supermassive or say a long-lived neutron star. And this is based on the criterion that the only the fluid element with a specific angular momentum that is larger than the specific angular momentum at the ISCO of the newly formed black hole can hope to stay outside, survive, and then contribute to the mass of the disk. And combining this criterion with not full binary star merger simulation, but idealized rotating neutron star model that want to mimic supermassive neutron star models, several authors concluded that as soon as you remove differential rotation from the core of your supermassive neutron star, you will end up in a situation where you should expect no disk formation. Okay? And this happens for collapse even earlier than 100 milliseconds. What we find here is that at the time of collapse, just prior to collapse, we have that essentially inside this line, all elements have a specific angular momentum that is too low to survive, so to stay outside of the black. So all this material up to 80, 100 kilometers should fall in the black. And if you remove this mass, there is not much mass left outside. So you don't expect, from this criterion, a disk mass of this order, but actually much, much more. But we do have a disk, and we do have a massive disk. So how do we explain that? Because there is the environment. This is not just supermassive neutron star, but there is all this environment, a dense environment, which also has this outflowing radial velocity that breaks the condition under which this criterion holds. And in the end, we can have a massive disk. So what we conclude is that if you have a strongly magnetized remnant, you can still collapse and leave a massive disk and maybe power a short multiverse jet, as long as there is this environment around you. And this might persist, or will certainly persist, for much longer than 100 milliseconds. So you can still have a massive disk for collapse even much later than what previously thought. Okay? And with this, I conclude. So I just go quickly through, say, take-home message. Numeric relativity is the tool to understand what's the mechanism, how to power a jet from a binary star merger, and what type of central engine, black hole versus neutron star. And we explored this fully explored the case of a neutron star with this very long simulation. And we have a highly magnetized system, and we've seen the separation of amplification. It was not possible to see before because just the simulation was not long enough, and this long simulation has shown this. We had hints of this emerging global structure, again enabled by the fact that we have a long simulation. And let me say here that we start with no colloidal field outside the neutron star. So this emerging structure is entirely due to the dynamics of the system, of the post-matrix system. And we have seen that strongly magnetized neutron star will be surrounded by this very dense cloud of outflowing material. In terms of jet, at 100 milliseconds, no signs of jet formation, but also not so favorable condition to hope that the jet will form at later times. And in terms of energy budget, rotational energy is sufficient. It's way more than what we need for a jet, if we could convert efficiently, but there is no efficient conversion mechanism at play, at least in what we've seen. And finally, this experiment of collapsing model shown that instead you could still form a powerful Blank-Snide jet with a massive disk and drill through the heavy ejector later. So this is supporting the black hole disk scenario. And also this last interesting point that you can still have a massive disk after collapse for times that are longer than what previously thought. So this calls for a revision of this kind of paradigm where supermassive neutron star will leave no disk soon after a few tens of milliseconds. And with that, I conclude. Thank you.